So we're kind of finishing up last time. We were going over this kind of ideas that you can have pure molecules that are either made of elements or compounds, and these are all kind of one species. So these are all so either all one type of atom or all one type of molecule. And that's a little bit different than the idea of kind of mixtures, which have a variety of different things. So if you had multiple atoms or multiple molecules together, then you would get something more like this kind of arrangement over here, where if you took two atoms, so if you had some carbon atoms and some, maybe some CO2 molecules and some H2O molecules and some maybe some neon atoms. You could kind of mix those all together and just have a mix of those different things. But this mixture would have all those different properties. It would have the properties of the water. It would have the properties of the CO2. It would have the properties of the neon gas, all those different things, versus a compound or an element. They all have one set of properties entirely, because this is all copper atoms, or this is all H2O molecules. So these are the pure substances. They kind of have only one set of properties because there's only one thing in them, versus the mixtures where you have multiple species all present. They're all going to contribute their own things. So if you took a mixture of sugar and salt, it's going to taste both salty and sweet. Versus if you had just the pure salt or just the pure sugar, those would be more compounds with just one set of properties. But that kind of leads to this idea of, what makes a compound different than just a mixture of the different elements, and why do compounds like H2O behave differently than just H's and O's on their own? And that's what we're kind of finishing up, kind of introducing this idea of these molecules are a little bit different. So if you look at compounds versus kind of the idea of mixtures of hydrogens and oxygen gas. So you could just have a bunch of hydrogen gas and oxygen gas. So you'd have some H's over here, maybe an O, maybe another H. You could just have a mix of those different types of gases, and that would just be two different gases, two different elements. They would have all the properties of oxygen. You'd be able to breathe it okay. It would also have all the properties of hydrogen, be very flammable. So you could kind of burn this gas, you could breathe this gas in, because it is just a mixture of those two elements together. And that's really, really different than if you actually combined those elements together and made water, which has this kind of shape to it. So we'll just draw it kind of like this, showing that those hydrogens and oxygens are actually linked together. And now this is a liquid at room temperature. So it's not a gas like the two gases are. It has very different properties than either of these two gases do, because this is a new compound. So it's not just a mixture of two elements, it's a new compound. And the reason this compound is forming is because these oxygens and hydrogens are actually hanging on to each other. There's actually a connection between those hydrogen atoms and those oxygen atoms that actually holds the whole thing together as one big molecule, instead of three separate, kind of looking like that. So we got this kind of triple molecule right here, three different atoms connected together, versus over here we have individual atoms that are all kind of hanging out on their own. And this is going to have really causes to have really different properties, really different behaviors by having those atoms actually physically connected to each other. And that's what makes compounds behave differently than their original atoms. Those atoms are actually combining together and producing a new molecule that we have. And if you were to do anything like trying to move this oxygen around, you would pull those hydrogens with it. Or if you try to move those hydrogens around, you'd pull those oxygen along with it. So you can't just separate out the oxygen from the hydrogen here. We can't just cut off one of the hydrogens, because then we wouldn't have H2O anymore. We wouldn't have water anymore. We'd have some new molecule, and we wouldn't have the original molecule we have. So this is kind of the smallest we can go. Water, H2O, the smallest molecule of the smallest amount of water you can have is a single H2O. If you have more than that, you have more water. But if you try to cut this any smaller, you won't have it anymore. You'll have something different. Versus over here, we can go down to individual atoms, because this is just a mixture of atoms together. So atoms in an element, when they formed up into a compound, you can't break them down any smaller. The compound is the smallest unit you can go to and still have that substance. And even for larger substances like a glucose molecule, the sugar in your cereal or in your coffee or anything else you drank with sugar in it today, it's a really big molecule. It's got 6 carbons, 6 oxygens, 12 hydrogens. It's pretty big. And that's the smallest amount of glucose you can have. The smallest amount of sugar you can have is 1 molecule of sugar. If you try to break this sugar molecule down anymore, it won't be sugar, it'll be something else. When it breaks down, it'll give you energy, but you can't actually go any smaller than that. Same thing with these other molecules. They're all the smallest unit you can get. And they're held together by various different types of chemical bonds. There's some forces that actually hold these molecules together. So like this CO2, that carbon and those oxygens are linked up with each other. They're physically held together by some forces so that you can't very easily separate out that carbon and that oxygen in the CO2, just like we can't break out the hydrogens from the H2O. These molecules are held together really, really strongly. And the reason why these molecules get held together has to do with these forces holding them together. And that force is due to the electrons in that atom. So when we look at a atom, we have the protons and the neutrons. Those are in the nucleus. So we'll just make a small atom right here. So this is a little atom. It's got 3 neutrons. It's got 3 protons. And then outside that atom, there's going to be some electrons as well. So I'll put the electrons out here. So the neutrons and the protons are all hanging out in the nucleus. That's the center of the atom. The center of the atom, and this is a pretty big nucleus. It's normally really, really small compared to the electrons. The electrons will probably take up the whole sheet right here. But this atom here has got a nucleus. It's got 3 protons and 3 neutrons in that nucleus. And then it's also got 3 electrons out in this outer electron cloud. If we were looking at nuclear properties for this, we could say, all right, well, if this got 3 protons and 3 neutrons, that means it has a mass of 6. It's got an atomic number of 3. That's the number of protons. So you could write this down as 6 over 3. You could write this down as a lithium atom if you want to. This is lithium, 3 protons, 3 neutrons and protons, total mass of 6. Overall, 0 charge. So this is just a lithium atom right now. But lithium atoms, all these electrons in this lithium atom could start interacting with other atoms as well. And depending on how these electrons in this lithium interact with other atoms, you can actually start to form new compounds and have this atom start interacting with another atom and form a new molecule. And sometimes atoms are pretty good about sharing electrons. Sometimes atoms end up taking electrons from other atoms. Sometimes atoms give their electrons away. It depends on what kind of atom you're working with. Some atoms love to give away electrons. They don't really like having them. They like handing away their electrons. Other electrons are a little greedy. They want as many electrons as they can. They're going to snatch them away. And some atoms are just really good at sharing. They're like, hey, you want that? No, I don't really want that either. Let's trade. And they'll share their electrons. But depending on what they do, whether they take or give or steal electrons, or if they share them freely, they're going to form these bonds. And that's how we're going to start to form compounds and molecules. So if you had a second lithium, so we'll just kind of draw, this is one lithium right here, and then another lithium over here. If they start to share their electrons, basically the space where the electrons live start to hang out and start to overlap. And if they overlap enough, you can actually form a bond that's going to hold those 2 lithiums together. So like in this case here, these 2 lithiums, their electrons are kind of near each other. The electrons end up overlapping and it actually forms a bond. Some atoms are very good at forming bonds. Other atoms not so good at forming bonds. So maybe if we instead have like a Cl atom right here, we got this Cl and this lithium here, they form a nice bond. They actually hang on to each other really well and we make a new molecule. But other molecules won't form so nicely. But it all has to do with the electrons in those atoms. And we can actually kind of figure this out by kind of looking at the atoms that we have. So whenever we're looking at an atom, looking at the periodic table, we can kind of predict some of the behavior of the electrons. We'd earlier looked at the behavior of the neutrons and the protons in terms of radioactive decay, how stable molecules are, whether or not they're going to stay together, whether or not they're going to break up, convert from one type of atom into another. And now we're going to look at the electrons, the outer part of the electron. Atoms are pretty good size, and most of the size from an atom comes from its electrons. So if you were to look at an atom, you would have a really small nucleus and then lots of space where the electrons are hanging out. Because the electrons take up so much more space, there's lots of opportunity for those electrons in one atom to interact with the electrons in some other atom, kind of like we're showing here. So when we're looking at kind of are atoms going to form bonds or atoms going to form new molecules, we want to kind of know how do those atoms behave, how do those electrons behave specifically. And generally, we only care about the electrons that are the farthest away from the nucleus. There's kind of like when you're in an atom, it's kind of like a stadium or a concert or a football game or a baseball game or any game where you pay for tickets. If you're really, really rich and lucky, or maybe you know somebody in the band or on the show, then you can get the really good seats and you can be really close to the stage. But most of us, we end up being stuck outside in the outer rings of the stage because we can't afford the good spots. So same thing for the electrons. The electrons are out in the far away parts of the stage. They're out farther away. But these electrons out here are the ones that are going to be interacted when another atom comes close by. If another atom was to come close by here, the electrons that are the farthest out are going to be the ones that interact first, because they're the farthest from the nucleus, because that's the part, just like if you have two cars, the mirrors, if you get too close to the next car, the mirrors are probably going to get damaged before anything else, because that's the farthest away, the kind of the part you get interacting with. So when we're looking at atoms, trying to figure out what is going to happen, is this atom going to bond to another atom? Is this atom going to form a new molecule with another atom? We only care about the electrons that are fairly far away from the nucleus. And it's actually really easy to figure out what electrons those are, because if you look at the periodic table, you can just kind of look at whatever row you're in, whatever atom you're working with, you can just kind of count how far over from the left side you are. So if you're working with an atom in this spot right here, this atom is 1, 2, 3 over from the left, and that atom has 3 electrons in that outer shell that are going to be interacting with bonds. If we're working with an atom in this row column right here, this one's only got 1. If we're working all the way over here, this one's got 8. So you can kind of count, and the same thing for the second row below it. Both this spot and this spot both have 1, because they're both kind of the first one from the left. Just like this spot here and this spot here both have 8, because they're the 8th spot from the left over there. So you can kind of count for any atom that you're working with. If they said we're working with one down here, just count 1, 2, all the way to 8. And we're going to ignore all these spots in the middle here. So we're not going to worry about any of these rows right here or any of these columns here. So if you're counting, you can just count kind of ignoring those. So if we were working with this atom right here, we would just say 1, 2, skipping all those, 3, 4, 5. So this would be a 6 in that case. So this is the 6th one from the left side over there, because again, we're going to ignore all those things in the middle there. So you can kind of just count the first 2 columns, count the last 6 columns. And those are sometimes called the outer shell electrons, the electrons that are kind of the furthest out from the atom. So even though some of these atoms may have lots of electrons, like carbon, for instance, carbon has generally 6 electrons. It's going to have 6 protons and 6 electrons from that atomic number up there. But if you were to look at where carbon is, carbon's in this spot right here, and that means it's in the spot that has the 4th. Oops. Zoom that out a little bit. Versus something like the oxygen. So carbon, if you were to look, is right here. Carbon is right here on the element table, and then oxygen is right here. So carbon is in that spot where there's 1, 2, 3, 4 electrons in the outer shell, even though it may have other electrons total. It's got 6 total electrons, but we don't care about all the electrons. We only care about the ones that are in the outermost shell. Sometimes these are called valence electrons. So either outer shell or valence are kind of 2 terms that you'll see to kind of describe how far those electrons are. And these, again, are the electrons out in the edge. So like if a carbon atom, if we're looking at it, it probably has 2 electrons inside, and then there's another 4 electrons a little bit further away, kind of further out, versus the oxygen's got kind of 2 inside, and then there's another, those were the ones with the good seats, and then there's another 6 that are further out. So you can kind of, as you get farther away, and if we were to go to a different atom, we'd see kind of further more up, but maybe there'd be some more up here. So kind of the farthest away are the only ones we care about. And that's basically telling you what column are you working with. Are you working with this column here? Are you working with this column here? You're working with one of those 8 columns there. Again, ignoring all that spot in the middle here. So for the oxygen, right, oxygen has an atomic number of 8, probably has 8 electrons total, but we only care about the column it's in. Turns out oxygen would be in this column here if we were counting it out. So we could always just look on our periodic table. If we're working with this atom down here, it would be in the 5th column. If we're working with this atom up here, it would be in the 1st column. So no matter what atom we're working with, we can just kind of look on that table and find the spot that it has. So you can always just kind of figure out the corresponding column that it's in, and then write down that that's the number of electrons we're going to work with. So these are what are called the outer shell or the valence electrons. And sometimes people will represent these differently. They may just say the number, so they could just read the number out loud or write it down. Other people will kind of do it to help out by showing it with these little dots. So we'd already said that carbon has 4 valence electrons. So you could kind of draw that, or oxygen has 6. So if carbon had 4, I'll write oxygen's 2. Oxygen has 6. So you basically draw it by just drawing a number of dots. So if you have 4 dots, that's like saying you have 4 electrons. Oxygen had 6, so I've already done 4, and then I'm going to start putting more around it again. So you can have kind of up to 4 on their own, and then as you go around a second time, you can double it up. So you can have anywhere from an atom with just 1 electron with 1 dot, an atom with 3 electrons, 1, 2, 3 dots. You could have an atom with 5 dots, so we go around 4, go around a 5th time. If you had an atom with 7, you do the same thing, 1, 2, 3, 4, 5, 6, 7. And then even for, if you had 8, you'd have 8 dots total. So depending on what atom you're working with, you could have different numbers of dots. If you had something with like 6, 1, 2, 3, 4, 5, 6, 2, 4, right? So you can have kind of any number of dots, and that's going to just be what position you're in, right? So if you're in that 1st column here, you only have 1 dot. If you're in the 3rd column, you have 3. So you'd see kind of different representations of that. So rather than just saying the number of dots, they'll just draw around your atom depending on what you're working with. Carbon has 4. So we see a carbon with 4 dots, just like this number 4 here. Oxygen has 6. You would see that way. So it's just a way kind of visually showing how many atoms, how many electrons in that valence or outer shell those atoms have. And that's going to help us later when we're trying to figure out how does carbon bond up or how does carbon form molecules, kind of knowing that carbon has 4 electrons to contribute from that valence shell, from that outer shell, will help us actually figure out the chemical properties of that carbon, how reactive that carbon is, what kind of bonds that carbon may form, things like that. Because what happens is every atom wants to try to get to 8 if it can. And it's going to get to 8 by either adding more things. So like oxygen right here has got 6 so far. It would really like to have 8 if it can. So oxygen's going to try to get to 8 by adding 2 more. So it's going to pick up 2 from somewhere else. Carbon may try to pick up another 4 to get to 8. Something like this atom right here, it could either pick up 7 or it could get rid of some. So you can also get to 8 by getting rid of electrons too. So somebody like this 2 right here, 2 would have to get to 8, it would have to get another 6. That's pretty hard to do, but it's relatively easy to hand away 2 of them. So if you had a whole bunch of stuff that you want to just get 1 or 2 more, you could borrow from people. But if you have very few, you may start giving away them because no problem with giving away some electrons too. So atoms are either going to gain electrons or give away electrons to try to get to the equivalent of either 8 or 0 dots. So they can give away until they get down to 0, or they could take until they get up to 8. But once they get to 8, they're going to stop taking. They're not going to take any more than that. Once they get to 0, they're not going to give away any more. So this one right here may just give away 1 and go from having 1 to none, and 0 is okay too. So either having 8 dots or 0 dots is what the atoms are trying to get to there. So these atoms are trying to get to the right number of dots, and they're going to do that by kind of changing their behaviors, kind of handing around electrons, and that's going to drive many of these chemical processes, forming bonds, forming molecules, forming new reactions. That's all going to happen as these atoms give away electrons and gain electrons from other atoms to form bonds. So things like H2O, CO2, all those molecules that are going to form is because these atoms are trying to get to have that full number of 8 or none around them. So this is just kind of showing a periodic table. So here's the nice little periodic table with a whole bunch of different values on it, different elements of various kinds. And again, we're going to ignore pretty much everything in this area right here when we're doing our counting. So we don't have to worry about all these middle electrons here, atoms. We're basically going, 1, 2, skip to 3, all the way to 8. So you can see that there's lots of atoms that would be drawn with one dot. You could draw this H atom right here with one dot. You could say H dot. You could also do Li with a single dot. Na like we did here, or even something like the CS with a single dot, right? These are all in that one dot column here. Versus the next column would be the 2-dot column. So Ra would have 2 dots, Be would have 2 dots, Ca, these would all have 2 dots. And depending on what row you're working with, what column you're working with, you'll get different values. So just like over here with the carbon row, carbon's in the 4-dot club, but so is Si. So we could also draw Si as a 4-dot atom there. And that's just showing that that's in that 4th column of things. All these elements here are in that 4-dot kind of column. And what that means is also for this, if carbon or silicon want to form a bond or form a molecule, they're going to either try to get rid of 4 electrons or gain 4 electrons to either get to 8 or 0. And carbon's kind of in that unique place where it could go either way without too much difficulty. Versus lithium, right? Lithium's only got 1 dot. Na's only got 1 dot. These both have 1 dot. They're probably not going to try to get 7 more. They're probably going to just get rid of 1 versus gaining 7. So they could either gain 7 electrons or they could lose 1. But it's a lot easier to get rid of 1 thing than it is to find 7 more. So they're probably going to go in this direction here. But they may not. They may do the other way too. You never know. But it's usually kind of just in terms of what's easier to do. Versus something down here, this Ne molecule right here. It's already got 8 electrons. It's already got 8 dots around it. It's in this column over here, right? Ne, Xe, Ar, those are all atoms that are in that 8th column right there. So Ar would do this too. Ar would have 8 dots around it. And that's saying that this has a full house. This is already filled up. There's no room in this particular molecule for any more electrons to come around. So this atom isn't going to form too many bonds. Argon, neon, these atoms are not going to form molecules with other atoms because they already have 8 electrons. And atoms form molecules by getting to 8 electrons. Well, this doesn't need to form any molecules to get to 8. It's already got 8 on its own. So all these atoms are relatively inert. Krypton doesn't react with other stuff. Xenon doesn't react with other stuff. It hangs out on its own. And these are sometimes called the noble gases, the gases that are a little bit snobby. They don't like hanging out with other elements. They all hang out by themselves and only themselves because they don't need to form any bonds to get more electrons. They already have all the electrons they need. They're a little rich in terms of their electron numbers. So they're not going to go and picking up other electrons they don't need to. So you won't see krypton bonded to anything. It usually hangs out on its own. You don't see neon or helium bonded to other stuff. It hangs out by itself. So these atoms don't need to form any bonds. But everybody else is trying to be like them. Everybody else is trying to get 8 electrons. So this fluorine right here, or this chlorine right here, they're going to try to find 1 electron to go from 7 to 8, because then they can be like these ones here and have 8 and be really, really, really happy. So something like fluorine with 7 dots is going to react with something else to try to get that 8th dot that it wants to have. So it's only 1 dot short of being at 8. And it's going to pick up electrons. It may steal an electron from somebody like this. It may share an electron if it has to. It's not going to give up any electrons probably because it's really hard to get rid of 7 when all you have to do is collect 1 more to get to 8. But that's going to drive this fluorine to form chemical bonds and form molecules with other atoms that also want to have 8 there. So we can kind of just do a little practice question here. Right? So we kind of talked about looking at a periodic table. So we'll open this one right here. So this was asking about the electron, the atom Ba. So Ba, barium, is an atom. So this is just an example of a periodic table. And it was asking about valence electrons, again, the outer shell electrons, or asking what column that you're in. And part of these ones are always just trying to find the atom itself. It's a little bit of a scavenger hunt. when you're looking at this. So there's a couple of B's. There's a BE up here. There's a plain old B over here. BR right here. So, kind of reading through. Oh, there's BA. So BA is right here. So lots of different B atoms. BE, BR, BE, plain old B. And then just kind of counting, right? What column are we in for these? So are you in the first column, second column, third column? We'll give you a couple more seconds for that. Okay, one more. So we'll give another 10 seconds there. So we found BA. That was the hard part for that. And then we count, right? So this is the first column here, the hydrogen, the lithium, the K, the CS, the FR. Second column, the beryllium, barium, BA. So this is the second column over. That's going to be our second list of electrons. So that one's going to have kind of 2 electrons total, and mostly everybody responded that way. So kind of counting along how many are over. Again, for some of these, then we'll do one more. So this is the aluminum one. So now aluminum is over this side right here. Aluminum right next to the B from before. But now this one, you have to remember when you're counting that there's some row columns that we count and there's some columns that we don't. So when you're doing a counting for something like aluminum, which is in this column here, you got to remember, definitely count the first, definitely count the second column. What do you do when you get to this kind of middle section here? And actually this one has extra numbers, so it does have kind of the, the counting all the way across, and then counting with version A where it doesn't count the middles versus the B's there. So you kind of count it a couple different ways. But again, for this one here, we're just going along trying to figure out how many electrons we have. We know that when we're on this column over here, there's 8. You can go backwards too if you want to. So if you know it goes 1, 2, and then 8, 7, 6, 5, 4. Aluminum would be in the 3 column again because we don't count any of these here. We go 1, 2, 3, and then all the way to 8 there. So aluminum was in that 3rd column there. And yep, everybody got that right. So we were good. So everybody got those right. So that's kind of a thing for kind of drawing dots. So if we're doing this AL, you were doing AL, you would put 3 dots around it. If we were doing the BE, you would put 2. So people did good with that. So kind of all these atoms, right? So like Cl, right? So chlorine over here, 7 dots we can count. So chlorine's got 7 dots. Chlorine really, really, really wants to have 8 dots though, right? 7 dots is cool, but 8 dots is way better for atoms. So chlorine's really going to try to get 8 dots. And what it's going to do is it's going to look around for other atoms to share. If it could get 8 dots on its own, that would be great. If there was just an electron lying around on the ground, this chlorine's going to snatch it up, no problem, they'll be happy. But that's probably not going to happen. Electrons don't just usually sit around waiting for chlorines to pick them up. But there are going to be other atoms that are also looking for 8. So chlorine's got 7, wants 8. It bumps into another chlorine that also really, really, really wants 8, but only has 7. And what these 2 atoms do is they decide to share. And these atoms are going to share their electrons. And they basically get close enough to each other that this electron here and this electron here are so close to the other atom that this green atom is so close to this black atom here that it's essentially hanging out with the atom there. And this black electron here and this chlorine are so close together that this chlorine's electron hangs out with the green chlorine. And it's like they're close enough to actually have the same number of electrons. So they're so close together that, the first one's got the 6 of its own. And then it's got 2 that are being shared between the other chlorines. So 1 of its own and 1 from the other chlorines. So by being close enough together, these atoms can actually share these 2 electrons. And if you were to count just the electrons from the green chlorine right here, or this one right here, right, there's 2, 4, 6, 7, 8. It looks like it has 8 electrons. If we ignore this one right here, same thing with here. If we ignore this chlorine for a second, this chlorine's really happy with 8. And then we can do the same thing on the other side and see there's 2, 4, 6, 8, or do it here, 2, 4, 6, 8. So these atoms get really, really, really close together. So if you're going to share electrons, your atoms have to be really close together. They have to be kind of almost so close that their electrons are overlapping. So you got one chlorine here and one chlorine here. And then the electrons that they share are being overlapped. So this electron spends some time with this chlorine and some time with that chlorine up there, but they end up sharing that pair of electrons. So they got 6 of their own and one pair that's being shared, and that's called a bond. Sometimes it's drawn like this with Cl. Rather than drawing 2 dots between them, they draw a line between them, and that's the same thing as drawing 2 dots, but it shows that those 2 atoms now are connected. So we're going to leave the other 6 electrons on their own. So this chlorine's got 6 electrons and 2 that are being shared, a total of 8. This chlorine's got 6 electrons and 2 that are being shared, a total of 8 as well. This is sometimes called a single bond. Single bond means that you're sharing one pair of electrons. You got one line between them, because other atoms may form more than one bond. But both of them get that full 8 electron out of this. 2 atoms sharing one pair of electrons. And that's a way that you can have atoms that get happy. They both get the 8 electrons they want. Before they were pretty upset. They only had 7. Now they've made it up to 8. And we can do that for all sorts of other atoms too. We can do that for the oxygen too. We could try to do the same trick. We see these 2 oxygens together. We bring them so close together that they form a bond, and we get oxygen with 2, 4, a bond, 2, 4. But that's not enough, right? We get so close that these 2 electrons, they hang out with each other. They start overlapping. That means that there's 2, 4, 6, but these oxygens still have 1, 2, 3, 4, 5, 6, 7 electrons. That's not quite enough. But what they could do is they could get close enough that this pair shares as well. And you end up with something more like this, where there's 2 pairs of electrons being shared, and then 2 hanging out originally. So we're going to share this electron here. We're also going to share this electron too. I'm just going to draw it like that to show. So you have 2 bonds for that. So this would be an O2 molecule. And you could either, maybe you'd see it drawn kind of like this sometimes, where they're saying that these are drawing 2 pairs of electrons being shared. Usually they just show it by 2 lines. So single bond would be 1, double bond 2. And you maybe be able to see where this is going. We could also have a triple bond where we have 3. So you can kind of share 1 pair of electrons, 2 dots. You could share 2 pairs of electrons. You could share 4 dots. You even could share 3 pairs of electrons with 6 dots. But these are just atoms that are trying to get to that full 8. So oxygen only had 6. It really wants to get to 8. Other oxygen also has 6. It really wants to get to 8. So they share 1 pair of electrons. They're both at 7, just like the chlorine did. Chlorines shared 2 electrons between the 2 each other. They went from 7 to 8. Oxygen tried doing that, and it worked okay. They went from 6 to 7, but they really want to have 8. So they're going to do it again, and they go from 6 to 7 and 7 to 8 by sharing 4 electrons between the 2 of them. So these 4 electrons are hanging out between the 2 oxygen atoms. They spend some times around oxygen 1. They spend some time around oxygen 2. But if you were to count how many electrons there are, right, this one's got 2, 4, 5, 6, 7, 8. And if we do the other side, 2, 4, 5, 6, 7, 8. They're both happy. They both got their 8 electrons because they're able to share some extra electrons between the 2 of them. And oxygen forms what's called a double bond. So double bonds, you're sharing 4 electrons. Single bonds, you're just sharing 2. And we could even go even one step further, something like this nitrogen, and have a triple bond. Nitrogen's got 3 different sets of electrons that can share this nitrogen. In this column right here has 5 electrons. It's in the 5th column. So nitrogen could do this. Phosphorus could do this. Arsenic could do this. All these different atoms that are in that 5th column there. They want to have 8, but they only have 5. And they say, oh, hey, can I borrow 2? Yeah, sure. Now we're both at 6. 1, 2, 3, 4, 5. Borrowed 6. All right, let's try it again. Now we're at 7. Let's try one more time. We got 8. So you could kind of draw this as an N with 3 lines between them. And those 3 lines are showing that you're sharing 6 electrons. So there's 2 electrons just hanging out with this N over here, 2 electrons just with this N over here, and 6 electrons that are spending some time on one side and some time on the other. So if you were to kind of look at it like this, there's 6 here, 2 here, and 2 over there. So you got kind of a Venn diagram thing. Nitrogen number 1 has 2 plus 6, right? 2 of its own plus 6 that are shared. Nitrogen number 2, 2 of its own plus that same 6 that are shared. And then the nitrogens are both happy because this nitrogen has 8, it sees 8. And this nitrogen over here also sees 8, the 2 of its own plus the 6 that it are sharing. So 6 shared electrons, 2 single electrons, that equals 8. Same thing for the other side. So by sharing electrons with each other, they form that triple bond between the two. So you could form double bonds, single bonds, triple bonds, all sorts of ways of kind of combining atoms together and sharing electrons. And that holds these atoms together really, really, really well. So if you were actually to try to grab this nitrogen, the other one's going to come along for a ride too. Because when you try to move one atom, all those shared electrons are being held on by both of these atoms equally. So if you pull on this, it's going to pull on the electrons and it's going to pull the other one along with it. So we're going to be pulling these electrons along. So these were all atoms of a single type, right? N2 or P2, O2. But this happens with any type of atom that we're working with. This could also happen with 2 atoms that have 5 electrons. Nitrogen has 5. So does phosphorus. So we could also have that same kind of thing happening for something like that. So just like N2 has a triple bond, NP, which are both in the 5-electron club as well, also would form a triple bond. So would a double P. If I had a phosphorus molecule with another phosphorus molecule, I could do something like that. So these are all in that 5-electron club. They're all trying to get to 8, and they're all going to get to 8 by sharing 3 electron pairs or 6 electrons total. So these are all different atoms that would have triple bonds. N2 is 1, so you could kind of have an N2 molecule here. This would just be NP, and this would be P2, right? There's 2 P's there, it's P2, NP. So these are all different chemical formulas for those different types of molecules, all of which may have a triple bond. So depending on what atom we're working with, we're going to have double bonds, triple bonds, single bonds. Every atom kind of has different preferences to try to help it get to that right number of electrons. And it's not just limited to 2 atoms. It's not limited to 2 atoms of the same type like we saw with the P's and the N's as well, right? You could have atoms that are different types coming together, just like NCl, NaCl, things like that. But we're also not limited to 2, right? Think of the molecules we've talked about. We've talked about molecules like H2O. We've talked about molecules like CO2. Those molecules actually have 3 atoms combined to them. We've only been doing 2 so far, but atoms also, more than 2 can combine. So something like this molecule here, Cl2O. This molecule has 3 atoms in it. It has an oxygen, and it has 2 chlorines. And we could go to our periodic table. Oxygen is in the 1, 2, 3, 4, 5, 6 row. Chlorine right here is in the 7-dot row. So oxygen's going to have 6 dots. Chlorine's going to have 7 dots. So we can kind of write those out, right? Oxygen's got 6 dots. Chlorine's got 7 dots for the 2 of them. And we could kind of try to figure out, based on this, can we put this together in such a way that we can make a molecule? And they're going to let us know that O is in the center. So generally, when you're looking at an atom, you don't know who goes in the middle. Generally, the first atom goes in the middle. So the first atom here is the oxygen. So we're going to put oxygen in the middle for that. If they don't tell you that way, that's kind of the convention. But if not, we'll always try to mention it on a test or a quiz. We'll say, you know, Cl3, C in the middle or something like that. We'll always tell you what's in the middle. Here, the oxygen we're going to put in the middle for that. So we got that oxygen in the middle. And we know oxygen's got 6 electrons on it. So it's got that kind of pattern there. And then we got to put the other two on. So we're going to put one chlorine on the side right here, and we'll put the other chlorine on the side over here. So oxygen's got 6. We know that the chlorines also have 7. So we're going to put the 7 dots around the chlorine. So that's 1. And then 1, 2, 3, 4, 5, 6, 7 dots there. And then basically what we're going to do is we're going to start sharing electron pairs, right? Everybody doesn't have 8. Chlorine's only got 7. Oxygen's only got 6. But if this chlorine and this oxygen share a pair of electrons, then that oxygen and that chlorine, this chlorine goes from 7 to 8 because it's sharing with the oxygen. This oxygen goes from 6 to 7 because it's sharing with the chlorine on the left. And look, there's another pair of electrons that we can make up over here. And that's going to make the oxygen go from 7 to 8 when it shares this electron here. So that's going to go to 8. And this one's also going to go to 8. Another way you could look at this is you can kind of basically think of it as a connect the dots game, right? This was a pair of dots, and we're going to connect those dots, either with a circle the way I did it or with a dot. And then you end up with this kind of molecule. So to clean it up, chlorine, single bond to the oxygen, single bond to the chlorine, and then we just got to put all our dots back on. And then what we usually want to do is we want to confirm that everybody's got the 8 dots that they're supposed to. So 2, 4, 6, and then a shared pair for 8. So this chlorine's good. This chlorine's got 8 dots. Do the oxygen next. 1, 2, 3, 4, 5, 6, 8 in the shared. So this oxygen's good too. And then the chlorine 2, 4, 6 plus a shared 8. So this molecule, everybody's got their 8 dots in the end. So even though they didn't have 8 to begin with, right? Chlorine only had 7, oxygen only had 6. By sharing the electrons, by rearranging the atoms in such a way that they can share their electrons, we've formed a new molecule where everyone's got 8. And this is a stable chemical molecule right now by sharing those electrons between the different atoms. So we're going to do that. And we can do this for single atoms. We can do this for pairs of atoms, triplets, lots and lots of different combinations. You could do this for a really big molecule with 6 carbons and 12 hydrogens and 8 oxygens if you wanted to. It'd be a lot of drawing, a lot of shapes. You probably have to be told how they're arranged and what kind of grid to do. But you could actually start putting together really big molecules. And these are just kind of some other examples here, right? You can see chlorine with singles, oxygens, nitrogens with doubles, triples. Even a molecule like this. This molecule has single bonds between the chlorines and the carbons, and then a double bond between the 2 carbons. But everybody's got 8, right? This chlorine's got 6 plus 2. This chlorine's got 8. And the same thing for all the others. 6 plus 2 is 8. 6 plus 2, 6 plus 2. And then we get down to the carbon here. 2, 4, 6, 8. And same for the other ones. So all these atoms, by various combinations, this carbon here is sharing all of its electrons, versus the chlorines are only sharing 2 of the electrons. So by different kind of sharing partners, sometimes double bonds, right? This carbon's got 1 double bond, a single, and another single. So it's got 4 bonds total. 3 atoms connected by 4 different kind of bond sets. 2 double, and 2 singles, right? This is just a single bond. This is just a double bond. All sorts of different ways to get up to 8. Just like this is 8 here by 6 plus 2 is 8. You can get to 8 electrons by a whole bunch of different ways. And you can form some pretty complex molecules in doing that. So this is just kind of some of the examples of ways you could get to 8, right? You can get to 8 by 3 and 2, or 2, 1 and 2, or 2 and 2, or 1, 1 and 2, 1 and 6, all sorts of different combinations that get you to 8. And the only other thing to kind of notice, we're always trying to get to 8, and that's going to be generally the rule. Everybody's going to try to get to 8. The only one that doesn't need to get to 8 is that first row here, this first row here. The far column, if you were to count, right, it goes 1, what we'd say is 8, but there's only 2. Helium's okay with just having 2 dots. Helium doesn't need 8 because helium's in that first row. But everybody else wants to get to 8. Helium and hydrogen are the only ones that are okay with 2. So hydrogen, helium, you can get to 2 dots and be okay. Everybody else is going to try to get to 8. So for this hydrogen here, even though it's only got 2, that's okay because it's on that first row. Everybody else wants to get to 8. So when you see things like H2O or HCl, the H is only going to have 1 dot or 2 dots, and that's okay. You don't need to get to the full 8. But everybody else wants to get to 8. And if you look at a periodic table, that can kind of remind you that, because while the second row has 8 and the third row has 8, the first row only has 2 blocks. So if you were to count across for hydrogen, you're only got to go to 2. You don't have to go all the way to 8. But everybody else wants to get to 8. Every other atom we're going to work with is going to try to get to 8, with the exception of the hydrogen heliums. They're okay with just the 2 there. So that's kind of this idea of drawing molecules out and drawing. What's going on here? There we go. So we can just kind of do 2 more kind of wrap up today. Kind of this idea of wrapping up some of the shapes. But you're always going to try to get to 8, unless you're hydrogen, and then you're going to try to get to 2. And these are some examples from a periodic table. So we can kind of look at all these different atoms. And if we were to kind of count along the nitrogen row, for instance, so we got nitrogen, hydrogen, CO, and F. So let's just jump to a periodic table. Oh, this one right here. So hydrogen is in that first row. Nitrogen's in the 1, 2, 3, 4, 5th row. Oxygen is 6. Carbon is 4. F is 7. So we can figure out all the different numbers for those. So we can just kind of write that down here. So we'll just kind of do that for each one of these. So nitrogen has 5. Hydrogen has 1. So we can kind of write that down there. The other thing we could do for this is, we can draw these dots, right? So nitrogen normally has 5, 3, 4, 5. There's a couple different ways to do this. And then we'll put the H's with their 1s as well. So we can do this by like a connect the dots type of method, where we just go along and say, okay, well, look, there's a 1 dot on this H, 1 dot on this N. Let's connect those and make a bond. There's 1 dot on this N and 1 dot on this H. We'll connect those, we'll make a bond. Same thing over here. So that's one way to do that. And then just double check after. Right, 2, 4, 6, 8, we're good. Hydrogen's only got 2, but 2 is okay for hydrogen. Same for the other ones. So that's one way to do this, is just to kind of do a connect the dots kind of technique. Another way you could do this, if you want to check or do it a different way, is figure out how many electrons we should have total. Right, the nitrogen has 5 dots on it, or 5 electrons. The hydrogens each have 1, but there's 3 of them. So if we were to count this, there should be 5. There should be 8 electrons total in this atom. This molecule here, 5 came from the hydrogen, 3 came from the hydrogen, 5 came from the nitrogen. There should be 8 dots total, and that could include things like bonds. And then you go and start drawing bonds. So we're going to put 1 bond here for 2. Another bond here for another 2, and another bond here for 2. So that's 2, 4, 6 electrons out of the 8 we have total. We got to put the other 2 somewhere. We're going to put them on the nitrogen here. And now we have used up all 8 of our electrons. And then checking, hydrogen has 2, hydrogen has 2, hydrogen has 2, nitrogen has 8. So 2 different ways of doing the same technique. It gives us the same result in the end. So whichever way you want to do it, some people like to do the connect the dots. Some people like to draw and then count and then add in extra electrons. Either way, as long as you don't add more electrons, you're okay. So you can't go put more than 8, but we did. We only put 8 here total. We can do the same thing for this kind of COF molecule. So this molecule has 2 fluorines, an oxygen, and a carbon. And they drew it out for us to kind of show where everybody's going to be hanging out, so we know where all those atoms go. And like we said on our periodic table, right, C, O, and F are in the 4th, 5th, 6th, and 7th column over there. So oxygen's going to have 6 dots. F's going to have 7 dots. So we could do a couple different ways. We could just do the standard, let's put all the dots on and then connect the dots. So 7 there. 7 here. 6, 1, 2, 6 there, and then 4 here. So that's one way to do it, right? We put all the dots down, 4 dots on carbon, 6 dots on oxygen, 7 dots on fluorine. And then we start connecting the dots. Connect one set of dots here, 1 dot here, 1 here, and then we have to do one more. So we're going to connect those dots as well. So it looks like we had a double bond to the oxygen and the carbon, and then 2 single bonds, 1 to the fluorine number 1, 1 to fluorine number 2. And if we were to count how many electrons, we'd be all set. So that's one way to do this. The other thing you could do is you could do it more of a kind of bonding thing and double check your electrons are all there. So we know carbon's supposed to have 4 electrons, oxygen's supposed to have 6, that comes to 10. 7 from fluorine number 1, 17. 7 from fluorine number 2, 24. So we should have 24 dots represented here. And we can just double check that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 20, 22, 24 dots. So all the dots are still there. We didn't lose any electrons. We didn't draw any by mistake. So either connecting the dots or start putting single bonds until you do it. So the other way to do this would be to kind of say, all right, well, let's, we have 24 dots total. So we'll put 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we put 24 dots there. But now what happened is there's not enough, right? The carbon doesn't have the full number, right? Carbon's only got 6. Everybody else got 8. So then if you're doing it that way, you basically move these and make it a double bond instead. So by having a double bond here, it's the same effect, but then that carbon still has the 8. So the connect the dots works a little bit better sometimes, but if you're just kind of putting down, you may get to the spot where you're like, uh-oh, I only got 6 here, but 8 everywhere else. I'm going to have to move a pair of electrons. And the connect the dot kind of prevents that from happening. But this is a way of kind of figuring out where electrons need to go. So if you end up running out of electrons with all single bonds, you're probably going to have to go to double or triple bonds. So if we don't have enough electrons, we have to start sharing more than one pair. If we have enough that we can just share one, that's okay. But we may need to share more than one instead, like we did here. So here we didn't have enough to give everybody a single bond. We ended up running out. If we had 26 electrons, we'd be fine. We could put the other 2 here, but we only got 24. So we're going to have to move that over because oxygen still needs to form 8, carbon still needs to have 8, and we can't do 8 and 6. We have to do 8 and 8. So we had to make a double bond. If we only had 22 electrons, we probably have to put a triple bond in somewhere as well. So as we start running out of electrons, we're going to start to do doubles or even triple bonds for that. But that's how we're going to kind of do these calculations, do these adjustments for all these different types of atoms going from one scale to another. So that's kind of this idea of atoms. And these are all atoms that are sharing electrons. So this line here means that that carbon and that oxygen are actually sharing electrons between each other. This nitrogen and this hydrogen, right? Sometimes the electrons hang out with the nitrogen. Sometimes the electrons hang out with the hydrogen. So this hydrogen's letting its electrons kind of be shared. This nitrogen's also got some electrons on its own, right? This electron's also got some electrons that only belong to it, but it's also got a pair that's being shared between the two. So these are all atoms that are sharing electrons. And what you may have noticed too is for everything so far, these are all the atoms that are in green on this periodic table. We're dealing with carbons, oxygens, nitrogen, fluorine, hydrogen. These are all the green atoms on a periodic table, and that's the atoms that are called the nonmetals. We'll talk about next time on Tuesday, we'll talk about how not only do some atoms share electrons, some atoms actually give away or take electrons, and they form things that have positive or negative charges. So that'll be kind of our next step. Talking about other ways that you can give electrons away and actually change the charge and end up with something like a Cl with a minus or an Na with a plus by actually giving away electrons and actually losing or gaining electrons to make a new atom with a charge. So this chlorine has actually extra electrons on it, becomes a little bit negative, while this one's a little bit positive. Those atoms are going to be attracted to and form a bond, but form a bond through positive negative interactions versus a bond that's formed by actually sharing electrons and a mutual attachment to that same electron there. So we'll do that next time, but for now, just kind of working with all the atoms that are on kind of the non-metal side, the atoms that like to share electrons, all the green atoms on this particular periodic table there. So that's kind of the thing for today. Let me just close that.